Section 1.2, Equations of Motion. In Section 1.2, we're going to look at the 5 equations for uniformly accelerated motion. In these equations, you can find one of several variables. You can find delta d, the displacement, v1, initial velocity, v2, final velocity, delta t, elapsed time, or acceleration. Which of the 5 equations that we will use depends on what's given inside the question. Let's take a look at sample problem number 1, and we'll decide which equations we will use to solve this problem. Sample problem number 1. 2 cars are on a straight road. Car A starts 120 meters ahead of car B and moves at a constant velocity of 7 meters per second forward. Car B moves at a constant acceleration of 2 meters per second squared forward. What they want us to find is how long it will take for car B to catch up with car A. So essentially, what we are finding is the elapsed time. Let's look at the information we have on car A and the information we have for car B separately. We want to know the distance or displacement that car A travels during this elapsed time, the time in which they catch up to one another. We know that car A travels with a constant velocity of 7 meters per second forward. Make some room here. That means its acceleration is 0. We know that car B travels from rest with a constant acceleration of 2 meters per second squared forward. We're looking at delta D, V1, A, and delta T for both A and B. For each of these, we're going to be using equation number 3. Equation number 3 states delta D is equal to V1 delta T plus 1/2 A delta T squared. Let's write down this equation. Since acceleration is 0, this entire section of the equation will cancel out. We are left with delta dA equals V1 delta T. We can sub in the only information that we know, which is delta dA equals 7 meters per second forward times delta T. For car B, let's put in all the information we can know. Again, we're going to use equation number 3, which is V1 delta T plus 1/2 A delta T squared. In this example, we know that it starts from rest, so this term cancels out. We are left with delta dB is equal to 1/2 A delta T squared. If we sub and solve everything that we know that the acceleration is 2.0 meters per second squared times delta T. We can simplify this a little bit. We know that, 1/2 times 2 meters per second squared is equal to 1. 1/2 times 2 equals 1. So I'm going to rewrite this as delta dB is equal to 1.0 meters per second squared forward times delta t squared. So now, let's see when they catch up to one another. We know that the displacement of car B must equal the displacement that car A travels during this time plus the 120 meter head start. So this statement, we can use it to help us find the elapsed time. And we're going to do that by subbing in delta dB and delta dA. So let's do that. We have, for delta dB, 1.0 meters per second squared forward times delta t squared is equal to 7.0 meters per second forward times delta t. I'll move this over a little bit. Plus 120 meters. So we're essentially solving for delta t squared, or delta t rather. And you can see that we have delta t in two spots. We have delta t squared on the left-hand side and delta t on the right-hand side. If we have both delta t squared and delta t as unknowns, this forms a quadratic equation. I want to rewrite this so it looks like a more typical quadratic equation to you. And then we can see how we're going to solve it. So for the time being, I'm going to ignore the units and the direction. They're both in the same direction, so it won't have an effect. And we're going to write 1.0 delta t squared equals 7.0 delta t plus 120 meters. To solve a quadratic equation, we have to set everything equal to 0. So we're going to bring 7 over this side and 120 over this side. When we do, we end up with 1.0 delta t squared minus 7.0 delta t minus 120. I'll get rid of the units. For simplicity, equals 0. Since this is a 1, I just want to rewrite it even simpler so that you can see this as delta t squared equals negative 7 delta t. Just realizing that I wrote t squared here. Minus 120 equals 0. Now, how do we solve a quadratic equation for delta t? Well, if there are two t's and one of them is squared and this is a quadratic equation, we have two options. We can factor if it's factorable, or we can use the quadratic formula. Let's try factoring first. If we were to factor, we would need to find two numbers that multiply to negative 120 and add to negative 7. And we would have delta t equals 0. Are there two numbers that multiply to negative 120 and add to negative 7? I can think of two numbers, and therefore we could factor this easily. Those two numbers are, if you have guessed, negative 15 and positive 8. Negative 15 times 8 equals negative 120, and negative 15 plus 8 equals negative 7. So now we have two answers. We have delta t minus 15 equals 0, and delta t plus 8 equals 0. If we rearrange this, we end up with delta t equals positive 15 and delta t equals negative 8. One of these is our answer. Since we are trying to find the time at which they catch up to one another, we have to reject the negative. There's no such thing as negative time. So our answer is 15 seconds. So we can write a statement. Therefore, car B catches up with car A after 15 seconds. In part B, we want to find the velocities of the two cars when they meet. We know that car A is traveling at a constant velocity of 7 meters per second forward. This velocity doesn't change throughout the entire trip, so when they catch up, car A will have a velocity of 7 meters per second forward. What about car B? Well, let's remember all the information that we had for car B. We know that car B started from rest, accelerated at 2.0 meters per second squared forward, and we want to find its speed after 15 seconds. What is its final speed? We're going to use the equation V2 equals V1 plus A delta T. If we sub and solve, we get V2 equals 0 plus 2 meters per second squared forward times 15 seconds. Punch this into our calculator. 2 times 15 equals 30. We have to write this answer to two significant digits. If we write 30 to two significant digits, we end up with 3.0 times 10 to the power of 1 meters per second forward. So our statement is the velocity of car B is 3.0 times 10 to the power of 1 meters per second forward, and the velocity of car A remains at a constant 7 meters per second forward. Sample problem number 2. A motorcyclist drives along a straight road with a velocity of 30 meters per second forward. The driver applies the brakes and slows down at 5 meters per second squared backwards. Calculate the braking time. So in this question, we're going to write down everything that's given. We know that the initial velocity of the motorcycle is 30 meters per second, 30.0 meters per second forward. We know that he's accelerating at 5.0 meters per second squared backwards. And we want to find the braking time. There's another piece of information that is implied in this question. We want to find the time it takes for this object, the motorcycle, to come to rest. we know that when it comes to rest, its final velocity is 0. So we need an equation that incorporates V1, A, delta t, and V2. We're going to use the same equation we used up above. V2 is equal to V1 plus A delta t. And we're going to rearrange this equation for delta t. If we do, we get V2 minus V1 over A. And we can sub and solve. V2 is 0 minus 30.0 meters per second forward over 5.0 meters per second squared backwards. Since we are dealing with vector quantities, we have to make sure that they are collinear. Lucky for us, forward and backward are along the same straight line. Only problem is they're not in the same direction. So we have to make forward and backwards in the same direction. We can either choose forward for both or backwards for both. We will get the same answer either way we decide. So I'm going to keep it as forward. Delta t equals 0 minus 30.0 meters per second forward. So that means I will change my acceleration to, if I flip the direction from backwards to forward, I will switch the sign or flip the sign to negative. So 5 meters per second squared back is the same thing as negative 5 meters per second squared forward. Sub and solve. Report your answer to two significant digits. We have negative 30 divided by negative 5. We end up with 6.0 seconds. Therefore, the braking time of the motorcycle is 6.0 seconds. Now let's determine the braking distance, the distance it takes or travels while coming to a stop. To solve for this stopping distance, we can use V1 V2. We know the acceleration, negative 5 meters per second squared forward. Notice here I wrote this as negative 5 meters per second squared forward, whereas initially we talked about it as positive 5 meters per second squared backwards. These two are equivalent. And we know the time it takes to come to rest is 6 seconds. We essentially have every single variable possible. So we can use many different equations to solve this answer. Any ones that include what is given and what is required. I'm going to use equation number 1, which states that the stopping distance is equal to V1 plus V2 over 2 times delta t. We can sub and solve, and we are left with 30.0 meters per second forward plus 0 divided by 2 times 6 seconds. We want to report our answer to two significant digits. 30.0 plus 0 divided by 2 times 6 is 90.0 meters forward. How do I write that to two significant digits? This is an example where we're forced to use scientific notation. There are too many digits here to report, and I can't simply get rid of the 0.0 because now I only have one digit and I need two. So if I write 90.0 as two significant digits, it becomes 9.0 times 10 to the power of 1 meters forward. Therefore, the braking distance is 9.0 times 10 to the power of 1 meters forward. We're going to continue using those 5 equations for uniformly accelerated objects. This time, we're going to look at free-falling objects. Whenever an object is under the influence of gravity, it is said to be in free fall. It's important to know that gravity imparts a constant acceleration of 9.8 meters per second squared down. This is called the acceleration due to gravity. We will use this information each time we solve an object that is free falling. Let's try sample problem number 3. A ball is thrown from a height of 52 meters from the top of a building with a velocity of 24 meters per second straight up. Determine the velocity of the ball at ground level. So let's draw a little diagram of what this looks like. We have a ball that is thrown up in the air from a height of 52 meters with an initial upward velocity of 24 meters per second up. And we want to find the velocity with which it hits the ground. So let's collect all the information that we know. First of all, we know that it's thrown up in the air with an initial velocity of 24 meters per second up. This ball will travel up to its maximum height and then fall straight down. When it does, its displacement, its change in position from where it started to where it ends is 52 meters and in the downward direction. So the displacement is 52 meters down. Since this object is under the influence of gravity, we know that the acceleration due to gravity is 9.8 meters per second squared down. And we want to find the velocity when it travels back down to the ground. So we have V1, delta D, A, and V2. Notice that we don't have the variable time. It does not exist. It's not given to us. So we need an equation from up above that does not include time. Let's take a look at which one we can use. If we examine these equations, we can see that equation number 4 has V2, V1, A, and delta D, and doesn't require time. So we'll be using equation number 4. Equation number 4 is V2 squared equals V1 squared plus 2 acceleration delta D. And we're going to solve this for V2. Right now V2 is squared. In order to have just V2, we're going to take the square root of both sides. So we're left with V2 is equal to the square root of V1 squared plus 2A delta D. We're going to sub and solve, and I want to make sure that our directions when we sub and solve are the same. We have both up and down. I'm going to choose down to be the direction for everything. So I'm going to write V1 as negative 24 meters per second down. I've changed it from positive 24 up to negative 24 down. Square this. Don't forget to square it. Plus 2 times 52. Sorry, let me put the acceleration in first. 9.8 meters per second squared down times 52 meters down. You'll know right away if you messed up the directions and the signs when you solve this. Because it's a square root, you can't take the square root of a negative number, so your calculator will let you know right off the bat that you've made a mistake. Let's punch this into our calculator and see what the answer is. If we punch this into our calculator to 2 significant digits, we should get the final velocity is 40 or 4.0 times 10 to the power of 1 meters per second down. So our statement, the velocity of the ball at ground level is negative 4.0 times 10 to the power of 1 meters per second, or 4.0 times 10 to the power of 1 meters per second down. In part B, we want to find out how long it takes for the ball to reach the ground. We know our initial upward velocity. We know our displacement, 52 meters down. We know our acceleration is due to gravity, 9.8 meters per second squared down. And we found our final velocity is 4.0 times 10 to the power of 1 meters per second down. Once again, we're in a situation where we have every single possible variable. So we can use any variable that includes time to find the time it takes to reach the ground. I'm going to choose a simple equation, equation number 2. V2 equals V1 plus A delta T. And I'm going to rearrange for delta T. It's equal to V2 minus V1 over A. I sub and solve. I'm left with 4.0 times 10 to the power of 1 meters per second down minus V1. Now watch what I'm going to do here. I'm going to switch the direction to negative down. So everything's in the down direction. Negative 24 meters per second down. Divided by 9.8 meters per second squared down. Punch this into your calculator and find the time it takes to reach the bottom. If you punch this in correctly, you should get to 2 significant digits, 6.5 seconds. Therefore, it takes 6.5 seconds for the ball to reach the ground. Have a try at the practice problems on pages 19, 20, and 21.